In this lab, we're going to add the capability to play against another human on a different computer over serial, so connecting by USB cables. In order to make this happen, we'll need to add code in several places. And this is a rather long lab. Now, fortunately, all of the code that we add outside of comms.py is actually going to be identical when we move to playing over the internet, which is a much more powerful, of course, communication architecture. So to get started with this lab, we'll need some hardware, and I'll show you what this looks like. We'll take USB to serial converters. These are special chips that can take the USB data protocol and convert it to serial, which is just a two-wire protocol, TX and RX. And you see here two different boards connected, TX on one to RX on the other, and vice versa. The third wire is ground, and that allows both boards to sit at the same voltage, which is important so that a high voltage is interpreted as a 1 on both boards at the same time. All right, so we'll connect these to our computer, and when we do that, you'll need to find the address assignment that Windows uses. And I find the easiest way to do that is to use the device manager and then look at the COM and LPT port setting. First with nothing connected, and then add your boards. So now we see that it updates to COM3. And the other one I connected is COM5. So for this demonstration, I'm going to be running two copies of Battleship, one using the COM3 adapter, the other using the COM5 adapter. I recommend this for testing, but if you want to try this out with an opponent, you would simply connect the other USB cable to their laptop instead. All right, so now we have this information, let's go ahead and get started with the code. If we look in the readme.py, we'll see there's 4 different files we need to touch: remote.py, comms, player state, and ship. Let's start in remote.py. So remote is a new kind of player. We've seen several players already: the human player and the computer player. The human player gets a guess from the keyboard. The computer player produces a random guess using our simple AI. A remote player, we have to retrieve their guess over the network, right? In this case, the serial cable. Each remote player has a pipe, and this is an abstract kind of two-way data pipe. In this lab, that pipe will be implemented as a serial connection, but in the next lab, this pipe will actually represent a TCP/IP socket. We don't care, though. It's just a data structure where we can write bytes into it and read bytes out of it. So I'll get a guess. By reading bytes out of the port, out of the pipe, RX bytes. I'm going to read an entire line out of the pipe all the way until the new line character /n. That represents the entire message. I'm going to take those bytes and convert them into a string using ASCII. So this will take the 1s and 0s and turn them into text. Now I'm going to take this text and convert it into a Python data structure, a tuple, which represents my guess. And the way I'll do this is with JSON. So guess is equal to, and loads, load s, right, load from a string, and the string is rxstr. At this point, I've got a guess, which might be 3, 4 or 0, 9. I'll just return the guess. Now, when I want to send a guess, I'll do the opposite. I'm given the tuple as an input parameter. And I need to encode this tuple as JSON, right, in order to turn it into a string. So txstr, and I'm going to use the dumps, which is the opposite of load, so dump to a string, the guess, and I'm going to append the new line character so that the receiver can use the read line function to grab the entire message. I'm going to take this string and turn it into bytes using ASCII. And then finally, I'm going to send these bytes out the pipe. And it's always best practice, in this case, to flush the pipe. We're only writing a few bytes here, and it might be the case that the operating system buffers up the bytes before sending them. We actually want to flush this out and make sure that our guess makes it to the opponent. So that's get guess and send guess. We'll need to do the same pattern for transmitting and receiving the player state. So we want to get the player state. It will look very similar to getting a guess. We'll receive bytes off the pipe. We know how many bytes to read because of the new line character. It says read until you get that /n. I'm going to take those bytes and turn them into a string using ASCII. I'm going to take that string and convert it into a dictionary using JSON. And now I need to take that dictionary and actually turn it into a player state object. So I will use the fromDict method. Now, note that this fromDict method is being imported. If we go up to the top here, we see that it's imported from player state. Remember this, you'll actually need to implement this yourself. How do you take a dictionary and turn it into a player state? That'll be next. But since we're already here, let's finish up this function. If this is the first time we're receiving our opponent's state, we won't have any history. So we'll just take their state for granted. We'll say, all right, our view of your state is exactly what you sent me. If self.state is currently none, I've never seen a state from you yet, I will take your entire state. On the other hand, if we've already played a couple rounds, I have a view of your state and I only want to update my state with a few values from your state. So if we look at player state, the update method only tracks newly sunk ships or whether or not the most recent guess is a hit. Right now, there's not a whole lot of value in making a distinction between simply receiving the entire state or updating an existing state. But we'll see in the next lab, where we want to detect cheating, we won't want to let the opponent move their ships mid-game. And so we'll only allow them to change portions of their state during the gameplay. So that's getting the state. Let's look at sending the state. Here we are simply going to convert the opposite way. We're going to go back down the protocol stack. So we'll take the player state and turn it into a dictionary using the toDict function, and the reveal parameter we'll set based on the value we get here. So we're given state and we're given reveal, and we simply use those to create the dictionary. Now when we're playing against a remote opponent, we don't want to show them all of our ships. We only want to show them the ships that are sunk. Unless it's the end, in which case we're going to reveal all of our ships. And so that's the reveal parameter. We'll see that the game engine, engine.py, controls whether or not the player should reveal their ships. At any rate, we have a dictionary. Once we have a dictionary, we can turn it into a string using JSON. And we'll add on the new line character to indicate that that's the end of a message. That will allow the other side that's getting the state to execute the read line. We'll take this string information, txtr, and turn it into binary data using ASCII. And as before, we will write this data out the pipe and flush the pipe. All right, and that finishes up what we need to do in remote.py. But we've seen we're already using some functions which we haven't completed. In particular, the ability to serialize and deserialize a player state object as a dictionary. So the ability to convert a player state into a dictionary from dict, and the ability to take a dictionary and create a player state from it. So we're using the toDict method to serialize it, and a fromDict method to deserialize it. Let's go ahead and go into player state and see how these are implemented. First of all, how do we convert a player state into a dictionary? Well, we're already given data as an empty dictionary. We need to add the key ships to it. And I need to go through all my ships and turn them, each in series, into a dictionary. I can do that efficiently with a list comprehension. Notice that I'm using ships here and not self.ships because the reveal parameter determines whether or not I should send all my ships or only the ships that are sunk. So if reveal is set to true, send all the ships. Ships is equal to self.ships. Otherwise, only send the ones that are sunk. Otherwise, I'll give away my hand to my opponent who may use it to cheat. The other key I'm going to add to my dictionary is hit, which will tell them whether the most recent guess was a hit or a miss. And then I'll simply return that back out to whoever wants it as a dictionary. On the other side, how do I use a dictionary to create a player state? Well, that's the fromDict method. Notice that this is not part of the class. This is outside the class. Because if it was inside the class, I'd already have to have a player state in order to call it. This acts like a constructor. I'm going to be given a dictionary, and this is going to produce a player state. So internally, it's going to call the constructor, and then it's simply going to set the attributes of player state accordingly. So state dot hit is equal to data hit, and state dot ships is equal to. And now I'll need to go through all these ships and append them to this array. I can also do it in one line with a list comprehension. And then I return the state. Now, I had to go through and manually put these pieces into state because the constructor doesn't accept them as parameters. If I look at the player state constructor, it doesn't take any inputs. It assigns default values for all these internal pieces. I need to go through and manually put them together. And then it returns the state. Okay? So we need to go deeper. I've used two functions here, ship toDict and fromDict, as part of my serializing player state. How do I convert a ship, which is a Python object, into a dictionary? Well, let's go into ship.py and find out. So here, inside of ship, there's a toDict method that takes a ship and converts it into a dictionary, or represents it as a dictionary. To do so, I simply have a key for every attribute. So there's a self.length attribute. I'll put that as the length key. Row is self.row. Column is self.column. Now, if any of these attributes were themselves complex objects, I would have to implement a toDict and a fromDict on those pieces, but these are just simple data types. In this case, integers, Boolean, and a list of integers. And so these can be converted directly into JSON without any problem. If I'm given a dictionary like this, how do I create a ship? So the fromDict is simply going to call the constructor with all of these as parameters. So return, and it's going to create a new ship using the values from the dictionary. Now, when I typically create a ship, I only specify the first 4 parameters to the constructor, but in this case, I'm given some hits as well. When I'm making a new ship, I don't want it to have any hits. And so we see, if we look at the constructor up here, hits is an optional input. And if you don't specify it, it's equal to none. And we see what happens here on line 35. When hits is none, it's an empty array. But if you do rpass a value here, we store it as a hit. So when I'm getting a ship that already exists somewhere else, I'm going to want to preserve that hit information as well. Okay, so that's going down the whole stack. From player state, how do you convert that to a dictionary? You use the toDict function. As part of that toDict function in player state, it's going to call the toDict for each one of its ships. At the end, you're going to get a dictionary representation of player state, which can be converted to a string, converted to ASCII bytes, and then actually sent out the pipe. So now we've finished remote.py, player state, and ship as far as serializing and deserializing them. The serialize means to convert into a binary pattern, and deserialize is taking the binary pattern and convert it all the way back up to objects. The other piece in player state we'll need to track, or to change, is the allSunk method. Let's see why. So allSunk tells me whether or not a player is lost. A player is lost when all their ships are sunk. Now that works well with computer and human players who I know all of their ship locations all the time, but for a remote opponent, I only know their sunk ships. They're not going to tell me the ships that have not been sunk yet. And so I'll naively think that the moment I have sunk the first ship, well, all the ships I know about are sunk, for ship and self.ships, right? I will turn true too soon. So I need to put a additional check to make sure that I've also know about all of the ships. So I expect my opponent to have ship type ships. If I don't know about all the ships yet, they're not all sunk. Remember up here, ship types is a list of each one of the ships. So I expect to have 5 ships, all 5 of which must be sunk. So this extra clause here is necessary for remote play to work. All right, we're almost done. The last piece, and the only piece related to serial in specific, is comms.py. So in comms.py, we either connect to the hardware as a server or as a client. I provided the code that implements the server logic. The client logic is much simpler. and simply echoes back the synchronization byte. So what's happening here, in serial, we don't have a synchronization logic. So we don't know when someone else is ready to play. In order to add synchronization, we'll have one side simply produce random values on the serial port and sit there in an infinite loop while true, sending out these random values. When it receives back the same value, it says, oh, somebody else is on the other side, now we're ready to play. And then we can start guessing and receiving player states. So to implement this logic, all I need to do on the client is, first of all, create the serial port. And this will be like COM1 or COM5 or something else, but I'm going to be given that as a parameter, port. And that gives me exclusive access to this. If I am using the serial port in another application, like PuTTY or another instance of Battleship, you'll get an error at this point, saying it's not available. But now I need to echo back the synchronization message. So server So I'm going to look for a message. And at this point, I've got some bytes. I could convert them up to an integer or do something else with them, but I really don't need to worry about it. I'll just write them right back out. So I'll echo it back out without doing anything else. And that's enough to tell the server side that, yes, we're ready to go. And rather than returning none here, I'll return device. So at this point, let's make sure we understand this comms file. If we collapse these two functions, we have host a serial server or connect as a serial client. These functions return two things, a priority and the serial device itself. Notice that when I host a serial server, I return a priority of 0, and the serial client returns a priority of 3. Every player has a priority associated with them. A human player has priority 2. A computer has priority 1. So you see I have priorities of 0, 1, 2, and 3. And in main.py, I use that priority to figure out who goes first. And this is important because we want to make sure one side is waiting to receive a guess when the other side is sending a guess. And when I'm looking at remote.py, I want one side to be executing send guess and have the other side be waiting in get guess. If both sides send a guess at the same time, those messages will be lost. They'll both be sitting at get guess, and there won't be any values coming in, and we'll have a deadlock. So we want to make sure that the order of play is the same on both machines. In this case, the serial client, whichever game starts as a client, will guess first. So in order to run this code, we'll need to, also check sometimes if you had a bad merge, you may see in main.py lines 102 and 104 have an extra parameter to display message. Just remove that extra screen parameter and it should be a simple you win or you lose. All right, so to run this code, we'll need to specify some extra parameters. So we'll go up to Python, and I already have a CPU, and let me just recreate this. So that's when I want to play the computer as an opponent. I'll click plus, make a new Python. Let's call this serial server. And the script path is going to be the same. It's going to be main.py. And then the parameters here, the type of game I'm going to play is a serial server. And the interface I'm going to use, the hardware interface is COM3. So click OK. We can see where that is used if I go up to main Notice I've added this command line argument parser. It has two types, two arguments, --type, or for short -t, and --interface, or shorthand -I. The type can be one of CPU, serial server, serial client. If you don't specify this, it defaults to a computer opponent, CPU. The interface is going to be the hardware adapter, a COM number. Based on these values, you see this if-else ladder, which takes the player type and figures out the correct object to use for them. If it's a serial server, I create the pipe using host serial server, passing in the interface, and use the file that's returned as the pipe for the remote player. In the same way, if it's serial client, I instead call connect serial client, again using the file as the pipe parameter to the remote player. Notice that I call it file here, but once we're in a remote, that first parameter is called pipe, and I use this pipe in get guess, send guess, get state, and send state. And I never actually worry or care or even know how this pipe actually moves data. In this case, the pipe is moving data over serial, but we'll find out in the next lab, we can create a different kind of pipe that actually moves data over the internet. And in remote player, we don't need to know the difference. Okay, so we can run this code, and if we do, it will simply block, and we'll have a black screen while it waits for our opponent to connect. Now, in testing, it's nice to be able to just play it with yourself and not wait for somebody else to come along that has also finished the lab. So let me show you how you can run the program in Anaconda. So here's my Anaconda prompt. I want to change the working directory. I'll give you a full screen view there. And then I want to activate my virtual environment that has Pygame and PySerial already installed. And now I can run the program, Python main.py, but I'll need to pass in extra command line arguments, -t, in this case serial client, and -i com5. Okay. All right. So it actually doesn't matter which side starts first in this case, but it's best practice to start the serial server code first. So let me go to a view where we can see both of these at once. If I run the serial server and then hit enter over here, we'll get both windows, and we can play Battleship. And you can get a hit for each opponent. And we can go back and forth. Now, if I were to play to completion here, we'd see one of the players would win and the other would lose. And I think it's a great exercise to go back and forth a few times with a keyboard. But whenever you're testing software, it's good to have an automation plan so that you don't have to sit here and play a bunch of games of Battleship to see if it's working. So let me show you how to automate this. So look in main.py here, and look at me. I can replace me with a different kind of player. Maybe a player that can play faster than I can. Perhaps a computer. So now, when I run this game, both sides are using the same code. I'm executing the same code in Anaconda as well as in PyCharm. So now both sides will be computers. One computer versus another computer. Let's try this out. So I'll hit play again. And now you can see the gameplay is automatic. Now it's a little slow, and why is it slow? Well, it's not because computers are slow. Computers are fast. In fact, they're too fast, and we decided last time that we actually wanted to slow down the computer artificially. Let's see what happens if I remove that delay. So that delay, if you remember, is just in computer.py. Get guess had this artificial sleep. If I remove the sleep, and then replay, notice the game proceeds much faster. Pretty exciting. And in fact, we can look at the document camera again and watch the bytes go across the wire. Let's see if I can change the view here. The back and forth corresponds to the guessing, TX and RX, for this two very bad Battleship players who are just randomly guessing. And so we see one side ended up getting the last hit before Destroyer was finally guessed an F2 here. All right, and that's the end of the lab. And now you're ready to play your opponent as long as you're within a few feet of them, hopefully 6 feet. No closer than that.